So the examples are something like this will be giving you OH, OH, which undergoes. So you can think that this particular OH bond is breaking and coming like that, and this OH bond goes away. Technically, you're taking out a water, so obviously this will be giving you a ketone. For this one, I'm giving you aqueous NaOH. Similarly, replace the chlorines, take out the water molecule like this, and the molecule that you're getting right now, its name is acetophenone. The other procedure by which you can obtain is by heating calcium, strontium, barium salts of fatty acids. So the general scheme is R C double bond O, okay. Remember, calcium is divalent, so the charge of a carboxylate is 1. That's why you have a 2 over here. If you heat this, then this leads to the formation of ketones, and as a side product you get calcium carbonate. So you can think technically you have to take out the unit of CO3 along with that calcium, and whatever is left behind you have to write is thing, okay. So if I just write the unit CO like that, now you think that you are taking out this unit, one oxygen here, here, and this calcium. So technically you are taking out this unit. Then what you're left behind with? R C double bond O and this R. And that is how you can think. Okay. So let's do some examples. Say I have given you CH3 COO whole twice Ca. Then obviously keep in mind which is your R. Your R over here is CH3. So it should be CH3 C double bond O CH3, and the rest would be CO3. Again, let's do another one. What is your R? This particular unit is your R over here, okay? An isopropyl group. So again, your answer would be what? and I will have CaCO3. If I give you this, what is your R? This is your R. So what will you do? And alongside the side product is calcium carbonate. The mechanism that you would be finding in books, okay, is something like this. You have a R, you have a O, you have a calcium. So basically you're writing the unit that I have written before, okay, just the molecule, which is your starting material. Okay, you just write a mirror image of this. So for that you again and now you try to think that you're taking away this unit, okay, which is something like this. I'm bordering the area for you. Okay, if you take out that unit, then obviously you can write that this will be giving you R C double bond O R, that is 2 molecules, and 2 molecules of calcium carbonate. That is your mechanism. Now, if the molecule itself has both the carboxylate groups, say something like this, then again, just remember what I have told you. Take out CaCO3. Keep the numbering in mind. So if this is say 1, 2, 3, 4, 5. So you'll be getting a 5-membered ring with a C double bond O followed by the side product calcium carbonate. Let us give it another try. Say I have given you something like that. Again, you just repeat what I have said. Try to take CaCO3. Then you are getting 1, 2, 3, 4. Try to number the carbons, otherwise sometimes you might be doing the right mechanism, but while giving the or drawing the ring, you might add extra carbon or you might lose one of the carbons. Okay, so numbering helps. Okay, the next topic. So this is basically one thing that you have to understand, that we are basically losing one carbon from here. So all decarboxylation processes, in all decarboxylation processes, we lose a carbon from the substrate, or you can say reagent. Let us study another decarboxylation process, which is the decarboxylation of beta-ketoacids. Okay. Now the name itself says beta-ketoacid. Now what does it indicate? If you have a acid group, something like that, say this carbon is the alpha position, then this carbon is your beta position. At this position there should be a carbonyl group. So this is your alpha, that is your beta, and such a thing is called beta-ketoacid. If you heat this molecule, then also decarboxylation happens and leads to the formation of a ketone. The mechanism for this process is as follows. Try to rearrange the chain which was flat before, okay, and try to make somewhat a six-membered ring like this. Now think that this particular pi bond is reaching out for the hydrogen. This particular sigma bond gets converted to a pi bond, okay, and this one breaks. So this unit out here, it is becoming carbon dioxide, isn't it? See, this particular is coming over here, so double bond O, that means this is becoming CO2, or to make you understand, let me draw it this way. This is your CO2, and what is happening to the rest of the molecule? What is this? This is a enol tautomerism, ketoenol tautomerism, and that is how you get your ketone. Okay, let us do some practice problems. Now, if you follow what I am trying to say, now what you do is you take out this particular unit of carbon dioxide. This hydrogen goes in here. That's all you need to do. That means the molecule that will form is something like that. That should be your answer. Again, I have given you something like this. We're applying heat. So again, what will happen to the hydrogen? This hydrogen goes in here and the rest of the thing becomes CO2. So minus CO2 minus CO2, and your answer will be this. Let us do another one. Okay, the more you practice different type of molecules, the more you will become an expert in such problems. Again, this hydrogen goes in here. So what will happen? So this is your CH3 and minus CO2. Now here you have been given a malic acid, right? So Just try to take out one of the CO2s. That means this particular hydrogen goes in here and the rest of the unit goes away as gas. That means your answer would be CH3, C double bond O, H, and minus CO2. Okay. Suppose I give you a molecule something like this. Now please understand, with respect to this particular acid group, this is alpha and this is your beta. But with respect to this particular acid group, okay, this is your alpha, that is your say alpha prime, beta prime, and gamma prime. Okay, so that means the one that is going to go away is only going to be the acid which is having, or which is the keto which is beta to this particular acid. Okay, so that means alpha and beta. So this particular acid is the beta-ketoacid, but this one is not. Okay, so in that case, this one goes away, but this one remains. Okay, number 6. I've given you this one, that one. Now you see both the acid groups are beta-ketoacid. Okay, so that means both will get decarboxylated. So here 2 molecules of CO2 will go away and you will be left with something like this. Okay, now a different type of question. I have given you a product like this. Okay, and I'm asking you, predict the beta keto acids from which this compound can be obtained. Now you see, if I take this to be the beta position, then this becomes alpha and this is also alpha. I'm just naming it as alpha prime. Okay, so what I will do is I will join a acid group in these positions. So I've joined one in the alpha position. I will join another in the alpha prime position. And one may think at this stage that the answer will be 2, but that is not the case. If you notice that this particular carbon is a chiral carbon, that means it can have 2 enantiomers. So it can have D and it can have a L from, that means 2 molecules here, the third being this one. So your answer would be 3. Expect such type of questions in integer. Okay. Next. Now we are going to do things that we have done in alkyne chemistry. So this is we are calling as J from alkenes. Okay. So basically what we are doing over here is called a reductive ozonolysis. Okay. The mechanism of which we have already discussed in the hydrocarbon chapter, so we are not going to be discussing it over here. So suppose I have given you a alkene like this, sorry, and my first reagent is ozone, followed by zinc in presence of acetic acid. All you need to do is disconnect this bond, cut this double bond or disconnect this double bond, write the two units and just join O. And that is how you can get your answer very easily. Okay. Say now I have given you or I have given you either of them if you treat with ozone. Now in place of instead of using zinc acetic acid, I am using over here something called DMS, which is called dimethyl sulfide. Its role is very similar to what is done by the zinc acetic acid, that is to act like a reducing agent. And both these particular compounds, if you disconnect them, the answer is the same, and you will be getting two molecules of this aldehyde. Okay. Now you do the same reaction, suppose with this particular unit. Now instead of using DMS, I'm using PPH3 called triphenylphosphine. Again, its role is very similar to that of DMS or that of zinc acetic acid. So again, acts as a reducing agent. So your answer over here will be one aldehyde and the other one is your ketone. Okay. The next one that we are doing is called a oxo process. It is also known as hydroformylation reaction. Okay. Only one thing that you need to remember is that terminal alkenes are converted to aldehydes. When I say terminal alkene, I mean something like this. Double bond is attached to the endmost carbon. Okay. And here the normal is major, iso is minor. Let's understand what is the normal and what is the iso. Now suppose the catalyst over here is CO2. CO is over here cobalt, okay, but CO capital is your carbon monoxide. Need some hydrogen, additional CO at a temperature of 150. Not really necessary to remember these conditions, but at least what the reagent or the catalyst is, one should remember. So it gives you R, CH2, CH2, CHO. So this is your normal product and is your major product. If I say iso, then I mean this product is your iso and it is your minor product. Okay. Let's do some examples. Just writing Wacker process to shorten. So this will be giving you CH3, CHO. This is one of your product which is major, and the other product will be okay. Similarly, you try the same thing for this is known as basically styrene. Okay, and your products obviously are CHO. Again, this is your major product and the iso product is the minor product. All right. Okay, just give it a try for practice with these. Same reagent. Same reagent. Now, this is known as Wacker's process. The above one and this one both are industrial processes. Here the reaction converts alkenes to carbonyl compounds. Now, always remember whenever you are doing questions on these type of catalyst, okay, so also remember that questions from coordination chemistry can also be asked in combination with these kind of organic reactions. Okay, so here the general reaction I'm writing for you. Again, you have been given a terminal alkene which is used in presence of PdCl2, water, CuCl2 and air, and it produces this. These type of compounds where there is a carbonyl and at the end there is a methyl group, these are called ketomethyls. Why these are important? Because they undergo iodoform reactions. Okay, so questions in combination in the synthesis of this and in combination with iodoform reactions may be asked in IITs, okay, or other competitive exams. So let's do some examples over here. Again, the R or alkyl doesn't change, so one has to keep that as an intact. Okay, and obviously this is giving you acetophenone from styrene. Same reagent will be giving you something like this. Same reagent will be giving you. Okay, so this is a very good method to synthesize ketomethyl groups from alkenes. Okay, now again this has been covered in alkynes and alkene chapter. Okay, so we are going to synthesize from alkynes ketones and aldehydes. Okay,